All right, welcome. And here we are, the final video of the course, video 2 of week 11. Next week is just the test, so this is it for material. And today we're going to talk about quantum optics. It's a subject that's very near and dear to my heart. I love the subject, but it's also a very involved and difficult subject. But we're going to get a kind of painted broad stroke picture of it and try to get a feel for some of the key elements of it. Unfortunately, we're not all going to be experts by the end of this, but we're going to hopefully see what the subject is and how it works, okay? So this is going to be a speed run, so buckle up. We have to do quantum mechanics and classical optics and quantum optics all in a few minutes, okay? So just try to pay attention to the key points. If you haven't seen some of the stuff before, that's okay. We're going to try to explain it as completely as we can in the time that we have. So we're going to start with the deep question of the course. What is light, okay? And, you know, we assume things are either spherical cows, apparently, or simple harmonic oscillators in physics. And we're going to treat light as a simple harmonic oscillator. Now, that's not totally unreasonable, right? Forget that you knew anything about light, but you just had very, very fast eyes. And you're fixed at a point of space as a monochromatic beam, as this laser was passing through you. What you'd see is an electric field which shoots up, and then it kind of slows down, turns around, shoots back down, slows around, and oscillates up and down about a point, as if there was some restoring force, right? And we know that, classically at least, there is kind of a restoring force from Faraday's law of induction. There's a magnetic field which is created, pulling the electric field back in. And we had this picture of light from the very beginning of the course where the electric field and magnetic field are twisting around each other as they kind of danced at the speed of light through space. And that leads to a fixed point in space behaving as if it was a simple harmonic oscillator that has a pull. So, what is a simple harmonic oscillator again? Well, it's described classically by an equation, F equals minus kx. We've already seen it in the Lorentz model. So we have F equals ma, that's m double x double dot, plus k times x is equal to 0. And it has solutions, cos omega t, that's cow, not cos, spherical cow, plus b sine omega t. We're reached the delirious point of the semester for me in teaching, and where omega, if we recall, was equal to the square root of k over m. So this is just the simple harmonic oscillator, and this is the picture of it. Now often we speak not only of, this is not true only for the harmonic oscillator, but everything in physics, we quantify it by its position and its momentum. Where it is and where it's going, that tells us everything about the system. Fundamentally, because Newton's equation is a second order differential equation, we need two initial conditions, and then we solve the universe. Not so with quantum mechanics or any finite computational power, but in principle, if we know the position and the momentum, we know everything. So let's take that approach to the harmonic oscillator. Let's say that it's maximally stretched. We have our mass here, it's maximally stretched at an amplitude x naught at time t equals 0. That's a difficult pen to write with. At time t equals 0, we have x of t is equal to x naught. Okay, so we plug that in and we see that that's cos of 0, which is 1, so it's a, and sine of 0 is 0, so that tells us that a is equal to 0. A is equal to x naught, rather. Okay, and let's take the momentum. So remember, the momentum is mv, or mx dot, and here that's going to be a times the derivative of this. So that's, what does it tell us? It tells us that the derivative of cos is sine, so it's going to be m omega times a times sine minus, rather, of omega t plus m times b of cosine of omega t is equal to 0. So we're assuming that at the very top of this thing it's at rest, so the momentum is equal to 0. So in this case, we get 0, so we get b, m times b is equal to 0. So we have b is equal to 0. And we have our full solution, x of t is equal to x naught cosine omega t. Okay? And we have the momentum, mx dot, which we just call p, the momentum, is m times the derivative of this, which would be, in this case, minus, based on our initial conditions, minus m omega times x dot sine omega t. Okay, so if we can look at x of t, it's going to be a cosine wave, and p of t is a sine wave, right? So one's max when the other one is 0, and vice versa. And what we're going to do is what's called we're going to look in phase space. Now, what is phase space? Phase space is just we're going to plot x of t versus p of t. And we can kind of already see what's going to happen here. So imagine we had x here and p. So at time equals 0, p is equal to 0. Down on this y-axis here, the p-axis actually, and we're at x naught. Then at some later time, cosine is going to go to 0, and this is going to be at a maximum. So it's going to be kind of like an elliptical plot, if I could draw an ellipse in phase space. Now what we often do in these things, because this is the case of a simple harmonic oscillator, we forget about the fact that it's a simple harmonic oscillator. It's actually just an equation that describes simple harmonic motion. So what we're going to do is we're going to define canonical coordinates, they're called. And we're going to normalize everything out. So let's let x of t, capital X, just be x over its amplitude, and capital P is going to be p divided by m omega x naught, okay? And in this case, let's just plot what we'd actually have here. We have x of t is equal to cosine, and sometimes, just to be cheap, we're going to say p of t, we're going to include that minus sign in here. It doesn't really matter, just so we have one sign versus another. So we have cos of omega t versus sine of omega t. And if we plot this, this is just a circular trajectory in phase space. So this is what a harmonic oscillator does. This is a simple harmonic motion. We're trading back and forth position and momentum. Okay, and we can kind of get that intuitively if we think about a mass on a spring. But what we're doing is we're going to look in phase space, and it's just going to be circular motion. So why am I talking about this? It's going to be a convenient way of talking about light. So we have light is modeled as a simple harmonic oscillator, or rather simple harmonic motion, and we're going to try to use this formalism quantum mechanically to understand the property of how light behaves. So let's do a speed run of quantum mechanics now, okay? So what is quantum mechanics in one slide? A bit of a tall order, but effectively we're just going to go cut right to the chase. So we have a system, and it's defined by some mathematical quantity called a Hamiltonian. Notice that little hat on top of the Hamiltonian. What does that hat mean? It means that it's not just a number necessarily. It can involve derivatives or integrals or other operations. We call it an operator, okay? So the system is defined by this quantity, which is an operator called a Hamiltonian. That's stuff. What about the state that we're trying to describe? Well, that's described by a wave function, okay? And there's a representation that you're going to see, if you haven't already in your quantum mechanics studies, where we can look at operators in terms of matrices and states in terms of vectors, okay? So an operator might be, for example, for a system which can be in one of two states, would be described by this 2x2 matrix. And sometimes you often see this term here called the Hermitian conjugate, M dagger it's called. And it's just, you take the conjugate of the matrix, flip the diagonals and the complex conjugates of them, okay? So this is a general property of operators, and we want to work in terms of matrices because it's a lot easier than working with wave functions. So we define this quantity called the ket, which is, we can represent it as a two-dimensional vector in this case, or in generally an n-dimensional vector, okay? And by the way, this ket is not exactly the same as the wave function. We can take the Hermitian conjugate of it and represent the wave function this way. So this is the relation between the ket and the wave function, okay? Where are we so far? Quantum mechanics described the system, the universe as a whole, has a wave function, or any subsystem of it we can describe as having a wave function, and the stuff in it, the system that it interacts with, is described by the Hamiltonian. So the Hamiltonian might have a matrix like this, and remember from linear algebra, the matrix has eigenvalues and eigenvectors. What's special about the Hamiltonian? Well, its eigenvalues are the possible energies of the system. So here we have two possible energies given by the whatever the eigenvalues of this matrix are. Okay, there's quantum mechanics on one side. That's everything we want to know. So we're just going to be dealing with these states, which we can represent as kets. And the system as a whole that we're studying can be described by this Hamiltonian, okay? So the electromagnetic field will have a Hamiltonian, and different states, such as a light bulb or a laser, will be will have a quantum wave function associated with it, or a ket. Okay, so let's move on now to the quantum version of a mass on a spring, of simple harmonic oscillation. So the quantum harmonic oscillator. Now, you may or may not have seen this before. If not, you'll see it in 323, I believe. This is the quantum harmonic oscillator has a Hamiltonian described by this. Okay, so we have to define what these things are. So h bar omega, which is an energy, by the way, if we look at the units of that, times this a dagger a plus a half. Okay, so this can be derived in the formalism of quantum mechanics. So let's try to pick that apart. So A here is called an annihilation operator. And an operator, remember, it does something. It operates on the state that it's in by removing one excitation. So if we have 10 excitations, we're going to get the square root of 10. Well, let's be easy on me, guys. If we have 9 excitations, we're going to have the square root of 9, which is 3, times 8 excitations. So it describes the operation of removing an excitation from the system. We can also have so that was an annihilation operator. We can also have a creation operator, which adds an excitation given by this same amount, okay? So an interesting fact, if we look in that Hamiltonian, we have an A dagger followed by an A. Like, forgetting about even the details of what it means, let's just apply that to a given, say we have 10 excitations or 27 excitations in our harmonic oscillator, okay? So let's apply this operator, A dagger times A on a state, N. Let's just close our eyes and do it. So we have a creation operator on A dagger N. And according to this, that gives us the square root of N times N minus 1 operations. And this is just a number. Maybe it's 9 or maybe it's 327 or some other irrational number. We can pull it outside, and this gives us the square root of N, not 2, it could be, times A dagger, this creation operator, on N minus 1. And just following what the rules tell us to do, we're going to get root N times the square root of N minus 1 plus 1, which is also just known as the square root of N, times N minus 1 plus 1. And this is going to give us N squared times N squared, which is N times the state. So this operation that we described, it doesn't actually do anything to this state. When that happens, by the way, just some jargon, we say that N is an eigenstate of this operator. But basically what it means is it doesn't do anything to it, but it returns a number. And it's kind of a probe that we can use to tell us how many excitations we have in our system. So let's just call this A dagger A the number operator. And if we apply the number operator to whatever the state is, it tells us the number of excitations we have in that state. So let's look at what this is now. We have this number operator in our Hamiltonian. And this is the Hamiltonian of the quantum simple harmonic oscillator. Here's our big leap. We're going to say that classically we can describe light as a harmonic oscillator. Quantum mechanically, we're also going to describe it as a quantum simple harmonic oscillator. And we can make use of this number operator and look at the Hamiltonian of the electromagnetic field. So we have h bar, which is an energy per photon. Remember that? H bar is the energy per photon. So it's the energy per photon times the number of photons. All right? So that kind of makes a lot of sense. The Hamiltonian, which is the energies of our system, tells us it's the energy per photon times the number of photons we have. But quantum mechanically, we get something else that tags along. We get this 1/2 h bar omega. And that's just a property of when we try to quantize a harmonic oscillator. We always have this extra ground state energy that just kicks around. In our lowest state, we have finite energy. This is even when we have the absence of photons, we call it vacuum. This is what we call a vacuum energy. And it's just predicted by formally deriving the Hamiltonian for light. So we understood our classical state as a trajectory in phase space. Let's do that in quantum mechanics. So we'll look at the quantum phase space. But we have a problem. Remember what our phase space was. It was a point in position versus momentum. And there's this little thing you may have heard of in quantum mechanics called the uncertainty principle. We cannot know the position and momentum simultaneously. We can, if we know the position perfectly, we have infinite uncertainty in the momentum, and vice versa. So we have this problem. We cannot have a point in phase space. Not a huge deal though, because we can define a quasi-phase space. Where we don't have a point in phase space, we have a blob in phase space. We have a region. So we can always talk about a region in phase space. The area of that region is h bar over 2 by h bar over 2. Okay, so that we always have an uncertainty within that blob, and that is fundamentally kind of unknowable, but we can talk about the region in phase space like this, okay? And that's called the Wigner function when we do this. When we plot that, it might look like this. This is a plot of the Wigner function. Okay, a plot of the Wigner function tells us our quantum phase space, right? So this is what a Wigner function, a state in phase space, it looks like a region in phase space, okay? And this Wigner function has an interesting property that if we look at kind of the shadow, the projection along, if we integrate all the momentum out, we get the probability distribution associated with position. And if we do the same with position, we get the probability distribution associated with momentum. And we can look at any kind of angle through phase space this way. So that's a neat property of the Wigner function. Okay, so that is a quantum phase space picture, and we can apply this to light. Now I'm an experimentalist, so I'm interested in how we actually measure this. It's good to put it in our notebook, but how we can calculate it, but how do we actually measure it? It turns out that it's actually very simple to measure this experimentally. We can do it with stuff that we already understand, okay? And it's a technique known as balanced homodyne detection, okay? What we're going to do is we're going to start with the symmetric beam splitter, 50-50 beam splitter. We know how to use this. So we're going to take the state. Here's our quantum state. And we're going to fire it into a 50-50 beam splitter. Okay. And we know what that does. It splits the beam in two. And what we're going to do then is we're going to interfere it with a strong, what we call a classical state. Basically a laser, like this. We're going to interfere with a state which has a well-defined phase relation with our state, but is very strong and classical. So this might be 1 or 2 photons. No way we could see it with our naked eye. We're going to amplify it, it turns out, by this strong classical state. Okay, beam splitter, we know how to deal with that. That's just a laser beam, and we're just going to put them both onto a beam splitter. And that classical state, by the way, we're going to call it a local oscillator. This is terminology that's been borrowed from radios and things like this when you actually use another type of homodyne detection. So finally, we have our local oscillator and our quantum state in question interfered at a beam splitter, and we're just going to detect them and effectively these things are interfering. We're going to detect them with photodetectors and subtract the photocurrent. Now, classically, what do we get? If everything's perfectly balanced and we subtract away the difference, we get nothing. But we cannot have nothing here, right? Nothing is impossible in quantum optics. We always have the background fluctuation. So it turns out what we get is almost a miracle when you work out the math. The photocurrent you get from subtracting these two detections is directly proportional to the quantum state, the quadrature of the quantum state. So if we want to measure the quadrature of the quantum state, we just interfere these two beams at a beam splitter, detect them and subtract the photocurrent, and we get like almost magically, it's crazy, we get a current I of t, and it's proportional to the quadrature wave function of this field, okay? And if we change the phase of this field, we can scan it, we can introduce a delay, we'll call it delta phi. As we scan the phase of this field, we're looking at different points on this Wigner function through phase space. So here's a picture of it, and kind of a cartoon of the idea. We have a quantum state, this strong local oscillator. Here it says there's a piezo, so basically something which introduces a delay to scan the phase. And as we scan the phase, we're looking at different slices of phase space of that Wigner function, okay? We actually physically detect a photocurrent, and that corresponds to a particular measurement. Okay, so let's actually take one thing out of there. Let's do this. let's put up our hand or a wall or something like that and block that so we don't get any light hitting here. Well, do we not actually get any light? That's not exactly true, because now what we have here is what we call the vacuum state, right? We have nothing here, but quantum mechanically, nothing is something. We have a vacuum state coming into this beam splitter. And what we should actually measure is that h bar omega over 2. And here's some simulated data of a homodyne detection of a vacuum state, okay? So even with no light, we're still gonna see these fluctuations. And here's the fluctuations you see when you do this experiment. You get this Gaussian distribution of quadrature fluctuations corresponding to the vacuum state. And this is what the corresponding Wigner function looks like of that state here. So we're actually going to get an electronic signal that sets our standard quantum limit, as it's called. Okay, so that's what we'd see if we measure the vacuum state. So we can actually calculate our variance, and that gives us our standard quantum limit. What about one excitation? We can actually send a single photon into here. Let's unblock it. And we'll send in a single photon. What would a single photon look like? Well, this is what it turns out it looks like. So here we have the Wigner function here, and a single photon state, the quadrature distribution looks like this. It turns out we have 0 probability of being at the origin in phase space. This is very non-classical. This is saying that whenever we measure, we get a random number, we get a random value for measuring it, but we never ever measure right at 0, 0 in phase space. So it's quite interesting, and this is what the probability distribution would look like if we measure that. And this is really what we get when we do this measurement, okay? So in practice, we don't quite measure a pure photon often, because we always have some probability of losing it. So what we actually see is a mixture of vacuum and photon. So here's some real data. This is some real data from a previous experiment I did measuring single photon states and the Wigner function of it. So on the left, triggered means that we've gotten a signal from our system that there's a photon there, and in the blue is the standard quantum limit, the background that we've measured vacuum state. And we see that we don't have 0 probability of hitting the origin, but a very reduced one. We get a state which does not look like this Gaussian distribution that we get from vacuum. And here is the corresponding Wigner function that we reconstructed with this state. So we can really measure this in the lab. Note this does not look like a classical state. But this laser, I mean, quantum mechanics is more general than classical mechanics, right? Or classical physics. So how do we, how does this generalize? And there's a quantum state. Well, if we look at this, it's actually quite different. And that is what is called a coherent state. And this is kind of the birth of quantum optics in the 60s when people, I think Schrodinger and someone named Roy Glauber was asking, what is the most classical quantum state? Like it has to somehow reduce to a laser or it has to reduce to a light field. How do we get the most classical state? And what they came up with was a coherent state. Now, coherent state is not a pure photon state. It's a mixture of photons. If you want to know the details, it's a superposition of different photons, and it has an amplitude, and it has some coefficients out front. So it's a sum of a bunch of different photons, some normalization in front, and it's not a pure photon state. It's a number of different photons. Okay, so this is the most classical state, and the amplitude is proportional to the electric field. By the way, therefore this value here is proportional to the intensity, right? So if alpha goes to 0, we have 0 intensity, we have our vacuum state back. And we've plotted that here for a very, very weak field. In fact, the field here, the alpha here is a half. So it's a very, very weak field. And we see a slight coherent wiggle here. If we can increase this to 2.5, we can start seeing it's starting to look more and more like a sine wave. And 7.5, we could really start looking like a sine wave. So what we can see, we can understand this as a classical wave with some quantum fuzz on it. Note that the quantum fuzz always has the same width. That's the vacuum, okay? That width is the same as a vacuum, and the higher and higher the amplitude gets, if this was this beam here, this would be the amplitude of the sine wave as plotted, keeping the same scale, would be like in the stratosphere. But the width of the fuzz would be the same. You wouldn't be able to detect the quantum fuzziness of it. Much like in current, you can't really tell that it's made of discrete electrons for sufficiently large current. So this coherent state is the quantum description of something like a laser. One more interesting thing that I want to talk about, and we'll wrap it up then, but a very interesting thing is squeezed light. Squeezed light is very cool. So the quantum Heisenberg uncertainty principle told us that was the product of the variance in x versus the variance in p was greater than or equal to h bar squared over 4. That was the Heisenberg uncertainty principle. It's an inequality, and it's not an inequality in a variable, it's an inequality in a product. So what if we make x very small, and then we just increase p to be very large, such that we respect Heisenberg's boundaries, and we say, okay, we'll have the product be greater than this or equal to it at best, but one of them is very small. It turns out you can do this. You can do this by making even pairs of photons, it turns out. We won't get into the details there because it's a bit of a heavy calculation, but you can make this in the lab. Okay, so we can do this, and this is called a squeeze state. This is the Wigner function of a squeeze state. And that might look like something like this. If we actually were looking at quadrature measurements and we're scanning the phase of the local oscillator, for some measurements we'd have more noise, but for some we'd have less. We'd have the vacuum level. And then if we kept scanning it, at some point we'd have less noise than vacuum, less noise than nothing, okay? And this is a real effect you can measure in the lab. This is actually a very useful effect. We heard it talk about LIGO, and they're actually looking at something called advanced LIGO, where they're looking at squeezed light to squeeze their measurement threshold even down further so they can detect fainter and fainter signals, because the lasers they use are limited by quantum noise. And by using squeeze states, you can reduce the effect of that quantum noise on your measurement. So this is something that they're actually trying to put in something like LIGO. So here we have some experimental data of an experiment I was doing a while back. We have a source of squeezed light and we're scanning the local oscillator. Often the noise, which is in decibels here, so 10 times log, is greater, much greater than what we'd see in the vacuum. But for certain phases, we have less noise than you'd expect from nothing. This is a very cool effect. So I could actually see this in the lab. I had my vacuum state, and by putting my hand in the beam, blocking light, I actually got less noise out than nothing. And putting it back in, there was noise. So this is an effect known as squeezing, and we can actually beat the Heisenberg uncertainty limit for particular values because it's based on a product, not a value. Okay, this has been a speed run through quantum optics. And obviously we haven't covered the whole field, but I hope we've touched upon the more fascinating aspects of the subject and whet your appetite for more. I'm always happy to talk about it. So if you want to send me an email or pop by when the pandemic's over and we're all back in our offices, then please do. And we're actually working on some experiments down in the basement now. So if you ever want to have a look at those, I'm very happy to show you. So let's summarize today's lecture. Classically, we can look at light as if it were a harmonic oscillator, simple harmonic motion. And quantum mechanically, we can extend that to look at a quantum simple harmonic oscillator and describe the electromagnetic field this way. Quantum mechanics, we have to treat things a bit differently. The system is described by this Hamiltonian matrix, generally just a Hamiltonian, and the state is a wave function. And it's an interesting thing is we actually get a Hamiltonian, a system matrix for the electromagnetic field, which is partly intuitive, the number of photons times the energy per photon, and partly very unintuitive, plus a vacuum term that just comes out of empty space. So we have to apply this quantum mechanics formalism to our classical view of the harmonic oscillator. And we can characterize a classical harmonic oscillator in phase space. In the quantum picture, we have to treat it a bit differently because we can't have a point in phase space. We have this quasi-probability distribution called the Wigner function, or quasi-phase space, and that's one way of characterizing our states. And we can measure that with stuff we already know all about from this course, a beam splitter and a couple of photodetectors. Subtract the photocurrent, and out comes our quadrature measurement. Okay, so we can have different states. Our coherent state is our most classical state that we could possibly have, right? It's like a sine wave with some fuzz on it. If we have a large enough amplitude, we don't notice the discrete nature of it. We don't notice the fuzz. We just see this field, which is what we expect classically. However, at the quantum level, there are states which behave very differently. For example, single photon states do not behave like little sine waves at all. They have zero probability of being at the origin in phase space. We can also beat the Heisenberg uncertainty limit for particular phases with squeeze light. And that has been our speed run through quantum optics. Thanks for everything this term, and we'll see you when we see you next.